Good morning. My name is Weihad. Before I start, I would like to thank our conference organizers. Thank them to give me such a great opportunity to present our work here. The title of my talk is Quantum Spintronics and Ferromagnetic Superconductor Interface. So this outline my talk. At the beginning, I will give you a brief introduction to the quantum interface. Then I will give you two parts. The first one is related to spin-triplet superconductivity at the interface, and other one is related to the zero-pi transition in these heterostructures. So before we start talk, let's first look at a particular interface. This is the interface between water and air. I think there is no doubt that the water at the top surface of the ocean is completely different from the water where below the surface. For example, the pressure will be totally different. Let's replace this with the ferromagnetic superconductor interface. What would happen? Let's first think about a ferromagnetic and a superconductor. For ferromagnetic materials, there's South Pole and North Pole. At the Fermi surface, the spin density stays for spin up and spin down will be different. So there's a spin polarization. It's between the North Pole and the South Pole, there's a magnetic field. It can generate a magnetic force. For a superconductor, let's say a BCS conventional superconductor, here's the BCS Cooper pairs forms, and they can travel coherently when the temperature is below the critical temperature, which means below such a critical temperature, the electron resistance is zero. Since this Cooper pair can travel coherently or for all the samples in large scale. There's also a magnetic field on this. If the temperature is lower enough below Tc, the magnetic field will be screened out. In other means, if we apply this magnetic field larger and larger, it will break the superconductivity. So let's think about when we put this superconductor and the ferromagnet together. If the superconductor meets the ferromagnetic, this ferromagnetic material is very nice. It's very pliant, it's the high first. And this superconductor will say, oh no, it's a ferromagnet, I better run away, bye. That means this a Meissner effect. For example, you put the liquid nitrogen into this drawer, this high temperature superconductor will become superconducting, and it will push the magnets away, bye-bye. So the question, can we put them together? The answer is simple, yes. How do we do this? We can use this brute force. In brute force, I mean by molecular beam epitaxy or sputtering, is thin film growth technique. We can grow these two materials layer by layer and put them attached to each other. Because of the interface bonding is so strong, and when we cool it down to the temperature below the superconducting temperature, these two will not detach from each other. So for most of the cases, the ferromagnetism will kill the superconductor, especially at the interface. However, there are always some exceptions. If the ferromagnetic material does not completely suppress the superconducting gap at the interface, which means the superconductivity at the surface exists, then the superconducting surface will be very, very interesting. The other means, if the ferromagnetic material does not kill the superconductor interface, it simply makes it interesting. So it does not kill you, makes you interesting. So this will generate two interesting properties in my personal view. The first one is the superconductor ferromagnetic interface. They will generate spin-triplet pairs. Due to this spin mixing and spin rotation process, long-range spin-triplet pairs were generated at the interface. The other one is zero and pi junctions. Because of this quantum interference between these two layers, the oscillating decay from the superconductor to the ferromagnetic materials will be oscillatingly decay. This oscillating decay will generate a zero junction and pi junction depends on the positive coupling or negative coupling between these two superconductors. If they are positive coupling, it means zero junction. If you are negative coupling, it's pi junction. So in this talk, I'm going to describe two results. One is related to spin-triplet superconductivity at the interface. The other one is related to zero and pi junctions. Let's first think about this first one, the spin-triplet superconductor at the interface. Because of this magnetic materials generate electric exchange, ferromagnetic exchange field, this will rotate the spin from the Cooper pairs, spin singular Cooper pairs, and this will generate a spin mixing effect, which simply rotates the spin polarization and makes it to be non-spin polarized spin triplet pair. If their spin rotation process happens due to spin scattering, they can generate the spin up and spin up and spin down and polarize the spin triplet pairs. So the K is at the interface, there's spin scattering and exchange field from ferromagnetic layers. So how do we detect the spin triplet superconductivity? The strong evidence is long distance Josephson coupling current in a ferromagnetic across a ferromagnetic materials. Let's say if a chrome oxide layer is a half metal metallic material, at the Fermi surface, there is only spin up polarized surface exists. So there's only one type of spin polarized current. There are two superconducting electrodes, now in titanium nitride, now in titanium nitride, and across this here, one can see Josephson coupling. Then there's another way to do this, which you use homophonium at the interface to generate inhomogeneous magnetization. Oh, back here, the way for the spin singular to spin triplet conversion at the interface was attributed to interface inhomogeneity property. Here, they purposely introduced the interface homogeneity and for the spin triplet pairs generation. As you can see, as a function of cobalt thickness, they can measure long-range spin triplet supercurrent here. So there are two critical challenges in my personal view. The first one is related to the interface inhomogeneous magnetization, because this is grown by thin film growth technique. If the interface is too good, too sharp, the interface mixing is small, which is not good for the spin triplet supercurrent generation. If the interface is too rough, then this will generate a spin triplet supercurrent. But this interface is very hard to control. You need luck. You need to be lucky enough to have a good interface for spin triplet supercurrent generation. The other one related to the detection. So in previous work, they can only detect it by long distance. If the distance is short, it is related to spin singular supercurrent. If it's a long distance, related to spin triplet supercurrent. So I view this distance as indirect evidence. So to solve these two critical challenges, our approach includes these two major replacement. So the first one is related to the interface. We replace this interface inhomogeneity with Rashba spin-up coupling. So by replacing the in space inhomogeneous, we replace the momentum spin texture. So the momentum space spin momentum locking we can use this to break the pairing spin symmetry of this superconductor pairing function. Then we can generate the spin triplet superconductivity. Advantage of this method is the rush bar spin upcoupling is controllable by many other means. For example, an external electric field can kill the rush bar spin upcoupling. So the second one is related with the detection. So in my view, the major difference between a single spin singlet pair and a spin triplet pair is that the spin triplet pair can carry spin angular momentum. So we can use the spin polarized current to probe the interface and measure the spin triplet and reflection if the superconductor is a spin triplet superconductor. So this is how we fabricate device and measure this to probe this spin superconductor at the interface. The material we use is NiFe nitride for the superconductor. The Ferromagnet material we use is 2D iron tantalum S2. It's a 2D layered material. And the interface, there's aluminum oxide thin barrier, which is critical. I will explain later. Then the interface rush bar spin upcoupling breaks the pairing symmetry and generates the spin singlet supercurrent and spin triplet supercurrent component. The 2D ferromagnet material has a Curie temperature of 80 Kelvin, is very metallic. At the low temperatures, there is a switching field is okay, not that large. And this is how we detect the spin superconductivity. We use the spin triplet and reflection. Because the rush bar coupling is broken symmetry when for perpendicular to this interface and parallel to interface. So if we inject the spin polarized current perpendicular to the interface or parallel to interface, the spin triplet Andrew reflection efficiency will be anisotropic because the rush bar is the spin momentum locking is in space parallel to the interface. So we can use the external magnetic field to control the magnetization of these ferromagnetic materials. This control the spin polarization direction, see whether it's perpendicular to the interface or parallel to the interface. Then we can put the device into external magnetic field at 9 Tesla. By rotating the device out of plane, we can measure the conductance at the interface to see at 90 degree and 0 degree with parallel, anti-parallel, when the parallel to the or perpendicular to the surface, the conductance will be different. So to be noted at 2 Kelvin, even at 9 Tesla, the NiFe nitride is also superconducting. As you can see, at science, we use a very small current to probe the spin triplet and reflection. When the temperature is higher above the critical temperature, the MR disappears. So this strong indication this MR factor is related to the superconducting properties. Furthermore, we can change the temperature to see this MR effect as a function of as a function of temperature under different external magnetic field. At 9 Tesla, the MR disappeared at 7 Kelvin. At 7 Tesla, the MR disappeared at 8 Kelvin. At 5 Tesla, the MR disappeared at 9 Kelvin. This disappearing temperature is strongly correlated to the superconducting critical temperature of this NiFe nitride electrode under different magnetic fields. As you can see, the right figure 9 Tesla, 7 Tesla, 5 Tesla, this is MR and the resistance and the critical temperature of the NiFe nitride, they are strongly correlated. So the MR disappears around the TC of the superconducting electrode. Furthermore, we can use bias voltage to measure the spin triplet and reflection to see how the chemical potential affects this MR effect. If the bias voltage is very small, basically we probe the in-gap states. This and reflection process probe the spin triplet superconductivity here. So it's roughly a constant. When the bias is much larger, and it probes the normal states in the electron band here, then the MR quickly disappears because this MR here, this normal here doesn't have the spin selection. So this is indeed what we observed. As a function of bias voltage, the MR first shows a constant and quickly disappears. This is a strong indication that our measurements indeed probe the spin and reflection at the interface. Furthermore, we change the interface barrier by changing the thickness of this aluminum oxide. As you can see, this due to rush-bar spin up coupling, this effective barrier will split to Z negative and Z plus depending on spin polarization direction. And the interface barrier strength is strongly correlated to the interface resistant air product. If the interface resistant air product is very large, the coupling is strong, which means in the tunneling region. However, if this is directly connected to each other, the coupling strength is 0, which means they connect to each other. So if the barrier Z is very large, the tunneling process is prohibited, which means the spin and reflection or conventional and reflection will be all suppressed. So the conductance is simply close to 0. The MR effect will be also extremely small. In other words, if the resistance is too small, the barrier coupling strength is almost 0. Then due to this rush-bar spin up coupling, spin up, spin down will be splitted. So one will be barrier, one will be lower. Then the MR effect will be also small. Only in an intermediate region, the Fermi level matches this spin down chemical potential. Then there is a perfect path for the spin polarized electron here. Then there will be a maximum MR can be observed. This is the theoretical calculation of this MR effect as function of rush-bar spin-up coupling and the barrier strength. As you can see, for two different spin polarization 0.7 or 0.42, for fixed rush-bar spin-up coupling, if we increase the barrier strength from small to large, they can cross a maximum region here. So this indicates this strong agreement with theory and experimental further supports that our measurements of the are indeed probing the interface spin triplet and reflection and the interface spin triplet superconductivity. So let me make a short summary of the first part of my talk. We use the rush-bar spin coupling at the interface to generate the spin triplet supercurrent. Then we use the spin current to probe the interface spin triplet superconductivity. And as a function of temperature, as a function of external magnetic field direction, we control the spin polarization, we cancel this MR effect. This is a result of the spin triplet and reflection to probe the spin triplet superconductivity at the interface. This work done was performed by my former student, Zhan Chai and Yunyan Yao here. Now let me move to the second part of my talk. It's related to the 0 and the pi junction. This depends on the coupling, positive coupling or negative coupling of the correlation, superconductor correlation here. In previous work, this 0 pi junction has been probed by the Josephson current here. This tiny device, superconductor, Ferromagnet barrier, and superconductor. By measuring the Josephson coupling in this here, they can observe this oscillation effect of this supercurrent. This indicates that the supercurrent is resulting from the 0 pi oscillations. For 0 junction and the pi junction, so my motivation to work on this is, can we use this spin current to probe them? So the method we use is related to this FMR spin pumping. This magnetization dynamics can be described by Landau-Lifshitz-Gilbert equation. And as you can see here, this damping term describes the Gilbert damping. Interestingly, when there's more spin current injected to this normal metallic layer and get relaxed, this generates an external relaxation source for the magnetization dynamics, which will enhance the Gilbert damping by adding extra enhance the Gilbert damping factor. So the more spin current getting relaxed in this material, the effective Gilbert damping will be larger. There's a device structure we may use is niobium pomeroy and niobium heterostructure. And this fMR signal measured at different frequency. By measuring the frequency dependent half-line width, we can obtain the Gilbert damping constant out. So this result will measure the Gilbert damping as a function of the pomeroy thickness above the critical temperature, 10 Kelvin, 15, 20 Kelvin. An oscillating effect was observed. This is related to the quantum interference of spin up, spin down electrons in the nickel iron. Is basically a quantum size effect. This has been explained very well in the theory by Milius in 2003. When the temperature is higher, this thermal broadening smears this quantum interference. For example, at 50 Kelvin, this oscillation effect will be gone. So more interestingly, when we cool down the temperature to 4 and 5 Kelvin, this oscillating effect is dramatically enhanced. A much larger effect is observed. What does this mean? Why the oscillation is dramatically enhanced the temperature is lower? Let's come back to this Gilbert damping and spin relaxing process. Firstly, a spin current is injected to the superconductor. Some spin current get relaxed, some spin current goes back to the Fermi layer. If there are more spin current relaxed in the superconductor, the effective Gilbert damping will be larger. So the question now comes to, what are the possible stones under the water that relax the spin current? What might be the difference for zero and pi junctions? What are the different stones here? So as far as I know, we know, there are 3 possible quasi-particle and relaxing sources for the spin current. There's conventional Bogolov quasi-particles and spin-triplet pairs and Andrew bound states. Based on because of time, based on our best understanding, we rule out this Bogolov quasi-particle and spin-triplet pairs. We believe, based on our best understanding, the most likely possible source is related to Andrew bound states. Because of the limited time, I will skip this description and jump to the major conclusion of our work. So we believe the reason is related to the density state oscillation in 0 pi junctions, which means for 0 junction, Andrew bound state level is at the gap edge. The spin current injection and relaxation needed to overcome this barrier. So less spin injection and relaxation happens. The spin enhanced damping factor is small. However, for pi junction, Andrew bound state level is at 0 energy in the ballistic region. Then the spin current can get injected and relaxed here. A larger damping factor will be observed. So here is a short summary. As a function of the thickness of this nickel iron, a large damping oscillation effect is observed. This is related to the related to the Andrew bound states difference for 0 and pi junctions. This is our best understanding so far. For example, if we further increase the thickness much thicker, this effect is gone. Yeah. So before I stop my talk here, I would like to acknowledge my collaborators. For the spin-triplet superconductor, we acknowledge Professor Shuang Jia, Professor Qingpeng Sun, Professor Igor Rudik, and Professor Xinzheng Xie. For the 0 pi junctions, we acknowledge Dr. Sihong Yang and IBM, Professor Yu Tao, and Professor Suyomi Shimakawa, and Professor Xinzheng Xie. What's more, I would like to acknowledge my 2 students who did this work and the funding sources which supported our work. And I would like also to thank the audience for your kind attention. I want to add one remark before I stop my talk. In my personal perspective, I think the interface between ferromagnetic superconductor interface is particularly interesting. especially for these 2D materials heterostructures. I think because of these interesting properties, more amazing physics and the results will be can be observed in the near future. So I look forward to see your results at this interface about the amazing physics and amazing phenomena or devices. And thank you again for your kind attention.